So we were supposed to discuss about reduction and oxidation reactions today. Okay. So first, let me start with oxidation reactions. Oxidation reactions. The first one, we will study these oxidation reactions as tests, as a part of test also. So check out. First one is shift test. Basically, shift test means it is an aqueous solution of uh, base, right? Base which gets decolorized, which gets decolorized by passing SO2, by passing SO2. What is that base? It is like this C double bond connected with this quinoid form with NH2 plus and Cl minus, and the other side will have a connection like this with NH2 on the other side here. So same way here also it is connected with NH2. Okay, this is called, you know, para para rosa aniline, rose aniline, para rose aniline. Got it? Clear. So generally this color of this solution is pink. Color of the solution is pink. Now this, when you add SO2, right, it will remain colorless. It will become colorless. So the same structure would be present for it. The same structure, while SO3 will get added here and SO3 will be added here while pushing this electrons. I mean, this pi bond was pushed here. So aromatic nature can be retained. This is how you'll get, and Cl minus will go away. So what happened here? All the rings got converted into benzenoid form. Okay. And this is the structure you will get. And this side of the nitrogen will also get substituted. And you will get this as S double bond O, double bond O, OH. And here also you will get just like an sulfamide form. So OH, just like a sulfamide form, SO3H. Okay. So this is the structure which you will get after sulfonation. Okay. In some books, this part is not given, that there is no amide form, only SO3H is being given. Point is, we need to get benzene rings because benzene rings keep this entire molecule colorless. And this is what we call it as Schiff's reagent. This is what we call it as Schiff's reagent. Okay. So once you have Schiff's reagent, that is, if you take this solution, okay, and then pass it through any aldehyde, right? If it retains the color back, that means it is going to be, and I mean, that is a test for presence of aldehyde. So this is the reaction that will take place. RCHO plus Schiff's base, or sorry, Schiff's reagent, which is colorless, and this will get reduced, and RCHO will get oxidized, plus this will convert into pink color. Again, pink color is being retained back. Okay. This time the pink color, because it is getting reduced, which means again this will become a quinoid form. So where you have NH2 plus, double bond, double bond, double bond here, and this SO3 will come out, converting into double bond here. Okay. Plus that SO3 will get reduced to form SO2 here. That's how it will get reduced, and RCO minus will get, RCHO will get oxidized to form a pink color form again. Clear, guys? So this is about shift test. So remember, shift test is observed for all the types of aldehydes. Okay. And SO2 is an acidic SO2 has an acidic character. So unlike other cases where other oxidizing agents, which we will be learning now, like toluenes and phthalines and all, they're basic solutions. This one is acidic solution. Okay, keep that in mind. Done. Next. Next, C. Second one, what do we check out is Baeyer-Villiger reaction. Baeyer-Villiger oxidation. PH C double bond O CH3. Achha, it is not only for benzaldehyde or benzene based, it could be for any aldehydes and ketones. If we react with any peroxy acid, OOH, this is peroxy acid, okay, then what is noticed is this oxygen will get inserted between this phenyl and C double bond O. This way, it will get inserted. So directly ketones are converted into esters. That is the advantage of Baeyer-Villiger. Mechanism wise, if you notice, it is like CH3 here, and this oxygen, which is peroxy group, that oxygen will attack here, rearrange to this. So we will have pH CO minus CH3 and O. This H I can transfer here with O C double bond O CH3. Okay. Again, the lone pair will try to push here, for which there will be migration of phenyl group. So this shows that the phenyl has better migrating aptitude than methyl, and this group will leave from here. So pH O C double bond OH plus and CH3 plus CH3 CO minus, which will take away this H plus, and from there we will get an ester form here. So this is a typical mechanism. This oxygen is the same peroxy based oxygen. Got it? So I suppose all of you understood that how the migrating aptitude works. Now, if you notice, the migrating aptitude is slightly different here. So migrating aptitude order is important. Direct questions will be asked here. What is the order in which the reaction happens? So check. Well, first is H, then this is 3 degree R, then this is 2 degree R. 2 degree R. Within 2 degree R, cyclohexyl will be more than cyclopentyl. Okay. Then this one. And after that, it comes phenyl. So phenyl has relatively lesser migrating aptitude than 2 degree, which is unlike what we see. Okay. Next, we have phenyl. So within phenyl, we can have better migrating aptitude with donating groups and only phenyl as compared to that of nitrophenyl. And then other than that, we have 1 degree R group and CH3 and RC double bond O. Okay. RC double bond O would be the least form if at all it is present. Okay. So let's see, out of all of these cases, with examples, it will be much easier to understand. Suppose if I have R, C double bond, C double bond O, R. If you have two double bond O groups here, correct? In that case, the migrating aptitude would be better, between these two. That is the only exception which you will have. That is, if you have R, COO, CO thrice H, then RC double bond O, C double bond O, R. Okay. This is typically the group which you will have. This is the only exception because O will come at the center. Otherwise, in all other cases, O will always take up on the other side based on migrating aptitude. So if you have double bond O here, then I use any peroxy acid. The peroxy acid will make these kind of esters. These are cyclic esters. Cyclic esters are also called as lactones. And if you notice, this one is alpha position, beta, gamma, delta. So it is also called as delta lactone. Okay. It is also called as delta lactone. Okay. Same way, if you have any group like this here in the presence of peroxy acid RCO3H, we'll get double bond O, and this side we will get connected and ester is formed. So in all of these cases, I'm sure you will understand how the scenario works. Suppose if there is an aldehyde here, for aldehyde, the migrating aptitude is better on this side. Sorry, OH. So acid will be formed here. Okay. Bear vinegar can not only be facilitated by, peroxy acids, it will also be facilitated by concentrated HNO3. Can be used as alternative. Can be used as alternative. That is, if you have a double bond O here and I use concentrated HNO3, because concentrated HNO3 will also release nascent oxygens. So we can expect first an ester formation here, cyclic ester formation here. Now see the importance of this. As long as concentrated HNO3 is present in excess, okay, that is sufficient enough. So again, it will react with concentrated HNO3. Open the chain here first. So what do we have? On one side, we will have acid, OOCOOH. And how many carbons we have? 1, 2, 3, 4, 5. 5 carbons we have. Let us write 4 of them. So 4, and the last one we have is OH. And you know that CH2OH in the presence of concentrated HNO3 will again be converted into acid. So that primary position will also again convert into acids. So this will again become COOH. So this is where you would end. Okay. So in case if you have concentrated HNO3 used as an alternative, then this will be the first step, and continuing that concentrated HNO3, this is the second step, and this is the third step. See, sometimes that excess is not mentioned. So just go with the options, whether the question is given more of an acid, okay? Is there anything that is been done after this formation of acid or something like that? So just be careful with that. Clear, guys? So this is about Bayer Villiger's oxidation. So I hope all of you got an idea about how to work, how it works. Right. Next, the third one. The third oxidation reaction is about reaction with selenium dioxide, SiO2. Earlier, if you recall, we already learned that when there is a double bond only, alkene only, and selenium dioxide is used, we'll get an allylic alcohol. This is what we used to get. Okay. But this time, if you have already an aldehyde present, okay, selenium dioxide in acidic medium, okay, CH3, COOH, okay, will convert this into glyoxal. So this is glyoxal. So it will oxidize the alpha position of the aldehydes. Okay. So suppose if you have a double bond OH here, again if I use selenium dioxide in the presence of acid, then I will have double bond OH, and here also we'll get double bond O. Okay, methyl glyoxal. Suppose if I take a ketone here, double bond like this, okay, and selenium dioxide is used. Okay, this will always oxidize on the more substituted side like this. This will be the major product. So it could have done on the either side. This will be major product. Okay, so this is dimethyl glyoxal. Dimethyl glyoxal. Got it? Usually, mechanism is not asked, but I'll just give you an idea about how it starts. Okay, so first we always expect to convert this into, okay, selenious acid. This is selenious acid, and imagine the same selenious acid reacting with an ketone here like this double bond O, which we will write in the form of enol. So imagine if at all I write this in the form of enol, OH. This is the more stable enol. So always remember the mechanism will drive towards the more stable enol. And if you have a more stable enol, now I have double bond selenium with OH and another OH here. Okay. So this OH, I'll write it a little away like this. Got it? So what would happen here is this H and OH2, OH and H plus will come out as water here. And from this end, it will convert, it will attack on the oxygen, which will try to push the electrons towards selenium. And by that, we will get CH3. Again, as soon as this happens, this bond will close because it has to make a double bond again. So I can expect this to convert as double bond O here with this carbon now has connection with oxygen with selenium having single bond OH. And now from here, the migration will take place. Okay. So this H minus will take away, sorry, this H plus will be lost. This H plus will be lost to make a double bond here. Okay. And what do we have here is this OH will take away this one, and we will get oxygen forming a double bond here. So selenium will take its electrons. So what do we get? Selenium will get reduced and H2O will form, and we will get double bond O. Typically, this is how the mechanism works. Just for reference, please remember only direct questions are asked. Okay. No, nothing else need to be known other than that. Okay. Now, these questions mainly, I mean, where the selenium dioxide questions need to be careful is where there is benzyl benzalic type of nature. That is, if you have a double bond O here, SiO2 is present, then in H plus. So you should understand that we need to make an adjacent double bond O. And the minute you react with NaOH with H3O plus. You know that adjacent double bond O, if at all we have, we need to think similar to that of benzyl benzalic kind. Benzyl benzalic kind, this group will migrate after baking. So we will get a 5-membered ring here with COOH and OH. That's it. That is the product form. Done. Now, these three are individual reactions, everybody. So, whatever we discuss, Schiff base, Bayer vinegar, as well as SCO2. These are individual oxidation. Now, we'll see it as a part of group. Within group, we have two groups. One is mild oxidizing agent, other one is strong oxidizing agent. So, first is the fourth reaction. So, mild oxidizing agents. So there are three mild oxidizing agents we need to deal with. One is toluenes, phthalings, and benedicts. Got it? So first let us discuss about toluenes reagent. Well, if we are taking AgNO3 and reacting with ammonium hydroxide, it will form a complex NH4 twice, sorry, NH3. NH3 twice plus and OH minus. Okay, this is toluenes reagent. If we react aldehyde plus 2 moles of Ag NH3 twice OH minus and heat sometimes is not facilitated given, but the idea is the same. We'll get that. So this is the product form: 3 moles of water, 4 moles of ammonia plus R COO minus plus 2 moles of silver getting reduced. This is Tollens test, or whatever we got here. This is the silver mirror formation. So if the silver mirror is observed, that means it is Tollens test is completed, or rather it is giving a positive test. Okay. Next, second, if you notice Fehling's test or Fehling's reagent, right? We need to have equal amount of two solutions here. We call it as Fehling's reagent A plus Fehling's reagent B. Got it? Basically, when we say A and B here, A will be aqueous copper sulfate and B will be sodium or potassium salt of, right, citrate ion. Okay, sorry, not citrate, tartaric acid. Okay, if you remember, tartaric acid structure would look like this. We will have this as CO minus, OH, OH, H and H. Okay. So we need to add 50% of this, 50% of this by volume. Okay. Both would be added 50-50 percentage, and this is called as Fehling's reagent. This is also called as Rochelle's salt. Rochelle's salt. Reaction is the same, whether it is Tollens reaction or the Fehling's reaction. So we will have this as RCHO plus 2 moles of copper sulfate in the presence of Rochelle salt, RS, Rochelle salt. It will give you RCO minus plus Cu2O. Okay. So if you take this copper sulfate in the presence of Rochelle salt, we have CO minus and CO minus. That makes it solution basic only. So this is also a basic solution. This is basic solution. So in the basic solution, this reaction is happening. Okay. Or let me write down better thing is I'll write down the complete equation. Right. Plus 5 moles of OH minus is giving RCO minus plus Cu2O plus 3 moles of H2O. That's it. Okay. Here Cu2 plus basically stabilizes the salt here, keeping the solution stable, where the connection will be like this: CH with OH and CH and CO minus, CO minus. And it is coordinated from all four directions of this group. So we have OH here and OH here, which is connected with CH, CH, CO minus and CO minus. Okay. This is how copper 2 plus is always exist in complex before the reaction. That's how it will be stabilized. That's the reason why we add Rochelle salt. As long as we have a stable complex, then it will slowly react with aldehyde and reduce itself to Cu2O. Now, next, let us see about failing solution. Sir, color of failings reagent. No, I didn't see the color here. Brick red here. Brick red PPT. Third one is about uh, Benedict solution. But the reaction type is exactly same. Here also we will have Benedict solution A, Benedict solution B. Correct? We will have Benedict solution A and Benedict solution B. Now, when it comes to Benedict solution, it is again aqueous copper sulfate, and this one is sodium and potassium salt of citrate ion. Citrate, citrate ion, right? Citrate basically structure would be like this, where we have CO minus, another CO minus, another CO minus, and here we have one OH group with Na plus, Na plus, and Na plus. Okay. One second. Let me just see the complex structure once.
Sir,
Yes, yes, Vito.
can you scroll up please?
Yeah. Sure. that's it. Yeah, yeah. Got the structure once. Check. Okay. So it's a little complex, so that's why I was searching for it exactly how it is. Cu2 plus connected from O minus and connected from O minus here with C double bond O, and here we have one OH group here, one OH group here, and then COO minus whatever we have like this with C double bond O. This way it is connected on this side, and here this is connected to the next Cu2 plus ion here like this with another O minus OC, which is connected to double bond O and another carbon. So basically what we are trying to observe here is this will have both CO minus here, and from both the ends here we'll have double bond O. Sorry, there is no double bond over here, direct connection. O minus and like this. Okay. 1 and 2 and CO minus will connect. This CO minus will connect. Hmm. So basically you would notice that this CO minus is connecting. This CO minus will connect from one end of a molecule here, correct? And another CO minus will connect from another molecule of sodium citrate. Got it? So my idea is what I'm trying to tell you out of this is check even this oxygen, and this oxygen. All these three are involved in complex formation. Okay. So sometimes it is asked that how many number of uh, connections citrate can give. Okay. So every citrate which has CO minus, CO minus, and CO minus, all of them are making a connection on all three sides. Got it? But not to the same copper. It will be to the different copper. Two at a time will give you, connection to one particular copper like that. Right. Anyways, the idea is the same, guys. The reaction structure is exactly same. There is no difference in Fehlings or Benedict. Both of them will give exactly same reaction and exactly same color. So brick red formation here. So that is a confirmation for Benedict test. So I hope all of you got an idea there. Right. Now these three tests, one is Tollens, Fehlings, and Benedict test, are exclusively for aldehydes, any form of aldehydes. If there is a double bond somewhere, it will not disturb. Okay. So, but this will also be observed positive when there is not only double bond, but there are groups which can not only C double bond O, which is aldehyde, it can be to the other, any other group which can produce aldehyde, like hemiacetals. Hemiacetals are unstable whenever we have uh, hemiacetals are unstable whenever we have a basic medium. So in basic medium, hemiacetals will also give the reaction. So like that, we need to just check out in what all cases we will get this reaction. Okay. So check first in which all cases they will give positive and not. Okay. So no reaction with double bond or triple bond by Tollens, Fehlings or Benedict. TFB if at all right means it is for all three. Okay. Right. But C triple bond CH, if terminal is there, okay, then it will convert into C triple bond C minus AG plus. So it will give white PPT with Fehlings, with Tollens and copper, which is the red PPT with Fehlings and Benedict. So in case if you find white PPT, the test is positive, but it is not giving a silver mirror test. So Tollens test can be observed by terminal alkynes, but not giving a silver mirror test. It is giving a white precipitate instead. Same way, a red color PPT if you are getting, but this time if it is with copper, not brick red, this kind of simple red is color if you come across, then that is going to be positive for Fehlings and Benedict test. Okay. Next is hemiacetal. Any form of CH, OH and all, OH and OR, that will convert first into CHO and gives positive test for Tollens, Fehlings and Benedict. So it will give positive test for all three. Next one, HCOOH, acid, okay, HCOCl, HCOOCH3, esters. All these three will convert into HCO, all of these three converts into CO2, CO2 and gives positive test, give positive test for TFB. So whether it is a formic acid and acid chloride or ester, all of these three will give positive test. Okay. Next, alpha hydroxy ketones. So if you have like this OH and double bond O, then it will get oxidized to double bond O, double bond O. So this is positive test for Tollens, Fehlings and Benedict. Okay. Now alpha hydroxy is there, but there is no hydrogen here, then it is negative test. So if you have double bond O, OH, and one more methyl is there. So there is no alpha hydrogen there. Then this is going to give a negative test for TFB. Okay, this is a negative test for this. Next, sucrose, starch, cellulose. These are all acetals. These are all acetals. And acetals will give negative test for Tollens, Fehlings, and Benedict. Got it? Glucose, fructose, mannose, galactose, um, what is that? Lactose, and maltose. These are the known ones. These all will give positive test for TFB. Tollens, Fehlings, Benedict. For all of these carbohydrates will give positive test. Got it? So in all of these cases, you should know that whether it is maltose and all of this, it will give positive test. Okay. Next, glyoxal, CHO and CHO, benzaldehyde. These two, which does not have, if you notice that there does not have an alpha hydrogen directly. So if this is a carbon, with respect to that carbon, I need to have a sp3 hybridized alpha hydrogen. As long as sp3 hybridized alpha hydrogen is not there, then they give negative test for Fehlings and Benedict, but they give positive test for Tollens test. Okay, Tollens. So Tollens is observed in benzaldehyde as well as glyoxal. Got it? And any form of acetals will be negative test for Tollens, Fehlings, and Benedict. Any form of this will be negative test. Keep that in mind. Furfural, if you notice, furfural is again similar to benzaldehyde, CHO like this. So this gives positive test for Tollens, negative test for Fehlings and Benedict, which is similar to that. So remember, these are the ones. Next, hydroxylamine are, you know, uh, NHOH. It will convert into RN double bond O. Okay, RN double bond O. And this will be positive for Tollens. Okay. Well, this is actually positive for Fehlings and Benedict also, but less observed. So I'm pretty sure this will not be included while asking questions. But if it is asked, mainly it will be asked for Tollens. So for Tollens, the reaction would happen. Okay. Next, if you notice catechol, so that is OH and OH. This one will give positive test for Tollens, Fehlings, and Benedict. Okay. Usually in cold condition. Cold condition. Imagine like this. You can write this in terms of its enol form. That is double bond like this with double bond O and OH. Okay. Now this will get oxidized. This part of double bond O, we can write it in terms of again, um, what do you say? Alcohol, I mean alpha hydroxy ketone, and that will get oxidized. Okay. And not just that, since catechol is happening, same thing will happen with hydroquinol also. So OH and OH for these two. The only difference here is these two will give you positive test at cold conditions, while resorcinol will give positive test for Tollens, Fehling's, Benedict, but in hot conditions. So we need to heat the solution first, then only reaction would take place. Okay. And if you have OH groups on all three positions here, then also it will give you positive test. So this is called chloroglucinol. Chloroglucinol will give you positive test for TFB. So the only differentiating factor for TFB, the only differentiating factor for TFB is this furfural and this. So that's it. If you know that, I think rest all cases you will be able to figure out. Please check if there is any doubt, we can discuss. Right. So this is about Tollens, Fehling's, and Benedict solution. Next is about strong oxidizing agents. Sixth one, I guess. What are all the strong oxidizing agents we will usually see? Let's understand that. Wherever you notice KMNO4, H plus, and heat, KMNO4, OH minus, and heat, K2Cr2O7, H plus, and heat. Okay. Concentrated HNO3 followed by heat, CrO3, H plus, and heat, H2CrO4, H plus, and heat. If you notice any of these kind of reagents given, then this is what we expect. If it is an aldehyde, it will convert into an acid. Okay, or acid ion, depending upon what you are reacting. You are reacting in acidic medium or you are reacting in basic medium. That's how the strong oxidizing agents will oxidize. Next, if you have a ketone, right? If you have a ketone on heating, first you will convert always into an enol form, and enol should be towards more stable enol. Once you get more stable enol, then you'll break the bond. After breaking, you make it as an acid. So what we will get here is double bond OOH plus HO double bond OOH. Okay. This is what is expected in, making an acid. And if you have like this, where I have, sorry, if you have like this, and first I'll make an enol, and then bond breaking happens. So we will get CH3, COOH from one end, and the single carbon should be always converted into carbon dioxide. Single carbon should be converted into carbon dioxide. Okay, that is one thing you should remember. This is called Popov's rule. I told you this before. what happens with the Popoff's rule. So I hope all of you understood what are the uh, you know oxidizing agents here. Next. Next you see nucleophilic addition reactions. Nucleophilic addition reactions. Sorry. First reduction reactions. Reduction reactions are also quite the same, which we all have repeated this. Wherever there is a ketone or an aldehyde, okay, there are two types of reduction we will see. If you are directly getting hydrogen and hydrogen here. So this reduction is done by four reagents. One is zinc, mercury in concentrated HCl, which we call it as Clemenson's reduction. Or we can do the same thing with NH2, NH2 and HCl. This is called Wolff-Kishner reduction. Or we can take thioglycol, thioglycol here, that followed by ranitidine, and this is called Mozingo's reduction. And lastly, red phosphorus HI. Okay, these four are the ones which are used. Okay, Clemenson's reduction, Wolff-Kishner, Mozingo, or red phosphorus HI. If you use this, we would get directly alkanes. Okay. If you do not want to get this, rather you will want to get into an alcohol part. Alcohol, then mainly we'll be using lithium aluminum hydride, sodium boron hydride, H2 by nickel or palladium. Directly we can use ranitidine nickel. We can use sodium in ethanol. Right. These are the reagents which we will typically use. There are more, but these are the ones which will be asked to you. Okay. I guess this part is clear, everybody. Reduction wise, not much, thing is observed here. But as an example, you got to note that in which case what to do. So suppose if you have double bond O here, got it, and double bond O here, and then I have NO2 here, and again I have OH here, got it. And let's say I'm reacting this with Clemenson's reagent, Wolff-Kishner, only lithium aluminum hydride, sodium boron hydride. In this cases, and lastly H2 by nickel, H2 by palladium, platinum, or nickel. In this case, what would happen? So if you notice in terms of Clemenson's reduction and Wolff-Kishner reduction, this will get first the double bond O will get reduced. At the same time, Clemenson's reduction will also reduce that nitro group into NH2. And as much as OH is concerned, this OH will be replaced by chlorine. Now, sometimes this is given as chlorine, sometimes it is given as alkane. That depends upon concentration of HCl. If you have enough concentration, that means it can give you alkane also. But go with the options. Usually, most of the time it is chloride given. Cl will be present on it. So Cl you need to check, and this NO2 you need to reduce into NH2 here. Okay, next. Wolff-Kishner. Wolff-Kishner, usually this NO2, they do not reduce, but in some cases, again, if you do not have any other option, then go for it. But alcohol should not be disturbed. That is more important part. In case of Wolff-Kishner, alcohol should not be disturbed. Okay. Next is lithium aluminum hydride. In lithium aluminum hydride also, you will see that this will get reduced, nitro will get reduced, but alcohol and double bond O will be reduced only to alcohols. Further reduction will not be taking place. And when it comes to SbH, sodium boron hydride, nitro is not disturbed. This OH will be the same, and this OH will be the same. Okay. Last, H2 by PD. H2 by PD, you notice that it will go very similar to that of lithium aluminum hydride, where this will be OH. This will remain OH, and here also it will remain OH. So mainly, this is the area that might be asked to you, like in which case, what has to be reduced. Okay. Let's see if at all I missed any reduction cases. That's it. Rest of the reductions, that acid reductions and all, we will come across carboxylic acid. These are the main reduction reactions which you need to know. Okay. Now, nucleophilic addition reactions, specifically on the conjugate side, is important for us. How on conjugate side the reactions will happen. Okay. Let me show you conjugate additions. I'll put it as a simple way to remember. One, if you notice there is a weak nucleophiles, they generally go for 1,4 addition. Generally go for 1,4 addition. Okay. If there are strong nucleophiles, they generally go for 1,2 addition. That is the first thing you should remember. Okay. Next. Well, we can actually categorize them into these cases. Okay. In which case it will act strong or weak. Whenever I say weak, you need to think as if there is a conjugation present in it. NO2 and NO2 is there, for example, like this. So this we can consider it as weak. Weak only in these cases, okay? It is not like weak nucleophile based on SN1, SN2 reactions. It is not that. Only in conjugate cases, what to apply, I'm taking those cases. That's it. Okay. So if you have double bond O, double bond O minus here, or I have RCH double bond CH O minus, or RCH double bond CH CH2 minus, or simply I have cyanide. And then if there is any metal which is present, for example, R2CuLi, okay, R2CD, and R injects in the presence of CuX. R injects in the presence of CuX. Clear? These cases, then secondary amines or tertiary amines, and CH3SH, if you have Cl minus, Br minus, I minus here, and yes, these are all, whenever you notice these kind of cases, you will observe these are all going to be weak nucleophiles. These are all the cases of weak nucleophiles. Weak nucleophiles only with respect to conjugate addition. Please remember that. Okay. If it has to go 1 to addition, okay, that means it must be strong nucleophiles. Strong nucleophiles include, okay, RMGX directly. If you have RMGX, no copper, lithium aluminum hydride, NaBH4, got it? NaBH4 in this case, and NaBH4 specifically in lot of cases, we might also add selenium trichloride to make sure it is always going to be 1 to addition. Okay, then RLI, and anything else. That's it. These are the cases wherever you see, you need to understand that this is going to go for, uh, 1,4 addition. Let me show you one example. Usually, if you are adding a carbon towards 1,4, then it is called Michael's addition. So, for example, if you have double bond O, beta diketones, and it is being given ETO minus Na plus, followed by 1,4 addition like this, double bond O, and here, let me put it this way, double bond O, and one more double bond here. So first, you know that minus charge will come here. That minus charge will always attack on fourth position. So if it attacks on fourth position, what do I get? This double bond will move, OH will come, and from here on this position, carbon has attached, and this carbon has double bond O, and a methyl group here. So this is the one which is formed, and this will undergo tautomerism. So as it get tautomerized, so we will get this as ketone. Correct? Now it depends upon, have we given the second mole or not. If we have given only 1 mole, you will end up the reaction here itself. If second mole is given, that means you will react this one also. This double bond also will be reduced. Okay. But this is where you would end. Correct. This is first example. Second example is Robinson annulation. Robinson's annulation. Okay. So here also we will have double bond O, and if you treat with OH minus followed by conjugate addition, so where we will have like this double bond O and double bond here, and this will give us X, and this X again if I react with OH minus and heat will give us Y. This is called Robinson annulation. In Robinson annulation, you will notice that first we will get double bond O minus charge here, and that will go and attack on 1,4 addition. Sorry, double bond is here. So 1,4 addition means it will attack here, double bond will move, this group will go. So that will give us X, which is double bond here connected with again double bond O, because first I'll get an enol form. I'm directly writing the keto form. Okay. This is the first thing which you will get. Intramolecular aldol can be observed now because internally you have again OH minus to be reacted. See the ring size 1, 2, 3, 4, 5, 6. So therefore, this minus charge will attack here, converting into a six-membered ring like this. We'll have now a six-membered ring with OH here, and after that we have a double bond O. And now this on heating, this is an aldol, it will undergo condensed form. And condensed form double bond will be this side with double bond O. So this is the product form. This is about Robinson annulation. Then next example is about HCN addition. So if it is given like this, as long as HCN is given, 5 degrees to 10 degrees are given, okay, in the presence of NaCN or KCN, then you'll only do 1,2 addition. As much as cyanide addition is concerned, you'll only do 1,2 addition. But if we take the same thing, HCN in the presence of NaCN, but this time if you are going about 80 degrees, in that case you will definitely do, now it is 1,4 addition. So this is 1,2 and it is 1,4 addition. So as the temperature increases, you will always go for 1,4 addition. Okay. Okay. Next, if you have HBr addition, that will also go for 1,4 addition. So you will get OH double bond with Br here, right? Which eventually forms Br here. Br here and double bond O. Okay. So that's how 1,4 addition has been happening. So I guess this part is clear when to take, 1,2 and when to take 1,4. Check out what is the order of conjugate addition. Order of conjugate addition will be like this. As much as there is huge support from the cross conjugation, it will have more 1,4 addition. Okay. So these are all for 1,4 addition. First amides, then esters, then ketones, and then aldehydes. Last comes acid chlorides. Acid chlorides. Imagine if there is no 1,4 addition. If this double bond is not there, then the order is exactly reverse. Okay. If there is no double bond, the order is reverse. Sir, will any yield of less stable enol forms? Sir, can we make it even if enol is not stable? Sir, can we make if enol is not stable? In which case, Arnav? Anudeep.
Sir, strong as well.
Hmm?
So
Why does? You stop there only.
why does it have more
More
1,4?
stability. Hmm? Acha, why does 1,4 happens? Is that the question?
Yes, sir.
See, my suggestion is not going to, that is based on molecular orbital theory. Okay, my suggestion is just remember the cases. Don't get into the details of it. Okay. So just check out in which case I need to go for 1,4, which case we need to go for 1,2. That's it.
Okay, sir.
And the last three cases which I have written are completely based on KCP and TCP. That is, lower temperature favors 1,2, higher temperature favors 1,4. Okay. Anudeep, any effect on NO2? No effect on NO2, even if there is benzene. Anudeep. That will get reduced. This has been, we already discussed this in alcohols also, one about NaBH4 and uh, LiAlH4. Cinnamic cases only, we will have that issue. Otherwise, we will not have that issue. Okay. So that is one thing you need to know. Other than that, did I miss anything?